Okay, so actually for building this total variation regularization, let's not do everything from scratch, but let's take a look at these older files written in the 2015 course that are available also online. And let's see what happens here. So first of all, we need to compute our continuum model, which for some reason this is okay, so here actually, and also this point spread function I think is now last times PSF, but let's just keep it there. So here you can see the original target of this year as a black solid line here, and the red is the convolved version. So then this was the continuum model computation and plot, and the next step would be to compute discrete data. And I think we could start with like 64 points. Okay, we should really change the in the plot function. We just have xlim. Okay, so here is a comparison of what the discrete model is giving us. So the continuum model is the solid red line, and our computational model, when we use our matrix and multiply these original signal evaluation points, put them into a vector and multiply that vector with the matrix A, you see the red dots here. So this is also showing that the computational model is not perfectly agreeing with the continuum model, but well, it shouldn't, because that's kind of impossible. It just should do a better job the higher n we use. So we can actually try to take, if you take a higher n and compute, you see that now they are better. For example, these guys here are closer. Here we still have some inaccuracies, but I think even that should get better if we use bigger matrices. So here you can see how the computational model is giving a better and better approximation of the continuum model when n is increased. And now I think let's just use n is 64 to start with and see what happens. So then if we do a naive reconstruction, so here we see that the naive reconstruction is doing an okay job, but I think we need again from the naive plot. So here we see that the naive reconstruction is giving rather okay results, at least a little bit correct. And from the inverse crime data, it's even pretty much perfect here. But this is too good to be true, actually. And now we can observe what happens when, as we have been talking, is so data. We should actually recompute the data. So like in computational mathematics in general, the idea would be that when we use a higher dimensional model, when we make n bigger, everything should hopefully become better and more accurate and closer. But with an ill-posed inverse problem, when we do that, well, we see at least here the computational model is now closer to the continuum model, so that's good. But if we compute the naive reconstructions, you see that from the data without inverse crime, even without noise, now the modeling error is getting amplified quite a lot, because the computational model is not so close to the continuum model. And with noise, it's even worse. With inverse crime data, so here the data has been really produced just by multiplying with our matrix, we see this incredibly good reconstruction. It's perfect. But it's only based on the fact that the data has been created with the same matrix we use in the inversion. Because you see, the noise immediately destroys our result. You see, the correct scale of things is like 1 and 1.5, and here you already see something like 600. Well, you can see the noise here. This is the noise. So it's not much. So this is what ill-posed inverse problems are like. Very small noise gets amplified incredibly. That's the core problem in ill-posed inverse problems. And that's why it's important to look at the singular values or the condition number of the matrix to see if there is ill-posedness. If there is, this is what happens. We can do a little bit higher still. Let's go to 512. When now we see that our computational model and continuum model are agreeing already quite nicely, because the numerical integration is getting more accurate. And naive reconstructions we have here, so this is from inverse crime data. Again, we have still a perfect one, which is not to be trusted, because even a little noise again blows up the whole result. The same thing than before. And here our computational model still has a little error, and when that error is blown up, we see here such instability. This is not so large in scale, you see, this is only 3, but still it doesn't really look very good. So that's why we need regularization. Now let's return in the data, let's go back to the 64 case, and let's go to Tikhonov. So we have here some alpha, and I'm actually using the SVD computation. We should compute the SVD, I guess, then. So this is these are the singular values. As you see, they are becoming small in the way we saw before. And then we can do the Tikhonov, because here I'm actually implementing the Tikhonov regularization using this filtering of singular values approach. So here you then see, again we have to change in the plot function. I wonder where is our data coming from? I think we should have 64, but why don't we? Take on 3. Oh, we should compute this one. And then this one. And then Tikhonov. No, we still have quite many. Why is the... Oh, maybe we should do this 5 as well. Okay, so now you see we are computing without inverse crime and with noise. And still we are getting this kind of quite stable result. So now we are kind of dealing with a regularization method. And I think this may be interesting to do. Let's see. Okay, let's just stop this. Sorry it's so confusing today, but I think let's go to this total variation regularization and let's see what happens. Let's see what happens here. So first of all, we are doing the minimization in a higher dimensional space. F is in the n space, but now we are in 3n, and I think I wrote the difference matrix, yes, with periodic boundary conditions. So then actually we are including a difference between the last and first evaluation point. So then there is one more row in the matrix. So the L matrix actually is an n by n matrix in this formulation. So then the unknowns are F, V plus, and V minus. And they are all in Rn. And the minimization is over all of them. So this is where we lose something. We have to do the minimization in a higher dimensional space. And it's a thing with optimization that it becomes more difficult when the dimension is higher. There is more room to search for the minimum. So this is something we lose. We have to minimize in a higher dimensional space. Then the top left block of our H matrix contains this ATA, this A transpose times A matrix, which we saw already in the normal equations related to Tikhonov regularization. And the 2 here is because MATLAB wants this 1/2 in the standard definition of the problem. Then we do the H vector that has alpha times 1s related to V plus and V minus, which are not the first n components. We have to do differently, but the remaining components from n plus 1 until 3n, they should be just 1s times alpha. That's for the linear term we computed on the blackboard. And then the first n components in the H vector, they are actually minus 2 times A transpose times the data. So this A transpose times the data is the one coming from the other term we saw in the function to be minimized. So then we do this L matrix. It's just a little trick how to do this matrix I showed that has just these minus 1s and 1s. So it's just a finite difference matrix for the first derivative. Then we have equality constraints. We have L times F, then just minus identity times V plus, and identity times V minus, because F, V plus and V minus are organized in one long vertical vector, or vertical vector with 3n elements. So L will multiply F, minus identity will multiply V plus, and this will multiply V minus. And on the right hand side we have just zeros. So because of some block matrix computation, you can see that this actually implements the equality LF equals V plus minus V minus. Then we have a lower bound. We actually have no lower bound for F in this deconvolution problem, but for V plus and V minus we will have zero lower bound because they are non-negative by construction. So here is the equality constraint. Here's the inequality constraints. We don't bound from above any of them, it's just infinity. And I think this just means we have just identity matrix and zeros, so we are not actually I think here we are pretty much doing nothing. Sorry, I don't remember really perfectly what's going on there. I think there was something that's not really so much needed in this part. What was it? But anyway, then we feed quadproc all that needs to be fed in. Sorry, this is so technical. And then we just save to the disk what results. So let's try this. Okay, and here also I think we need okay, and now actually I think we should move to the higher dimension to get more sense out of the computations. So let's again compute the discrete data, maybe now with 128. Run it, and then I think we need to run the naive computation. And then maybe we can already compute the total variation. Let's see. Let's see if we can do it even with 256. Maybe it starts to look better in that case. Okay, so now you start to see that there really is this kind of tendency to do piecewise constant results. And we also see in this smooth part of our signal, we see the typical staircasing effect of total variation. It kind of tries to do everything with piecewise constant as much as possible. And then let's use a bigger alpha, so we are emphasizing the regularization term more. Let's see what happens with that. Now you see it's kind of even more piecewise constant. It tries to jump in fewer places and be really constant, but also here we are starting to lose the amplitude, the correct amplitude. And also here, well, the staircasing it's pretty much the same, but also here it's not really recovering so well, this one. So now we are starting to lose, it's trying to also make the jumps smaller, because the TV norm is the number of jumps, well, it's kind of just summing up the sizes, absolute sizes of the jumps. So now that we are trying to make the TV norm smaller, it's trying to do it by making smaller jumps. So we see that it's not really reaching for the extremes anymore, and the staircasing is getting worse. So that's how total variation looks like. I think maybe we can, if we compare to generalized Tikhonov, why? No. Tikhonov. So generalized Tikhonov, where we have also a derivative penalty. If there we now penalize the 2 norm of the derivative instead of the 1 norm, you see that this is what happens. We are enforcing smoothness. Again, it's not with a large regularization parameter, it's not really reaching for the tops and bottoms of the amplitudes, but it looks very, very different qualitatively than the total variation. There are no jumps. It's really smooth everywhere. So it's really not finding the jumps at all. But arguably, in this smooth part, it's much more like the original signal with no staircasing effect. So here we are comparing, penalizing the derivative with either 2 norm or 1 norm, and as you see, the results are very different. And in the exercises, you have the pleasure of looking into this deeper. Okay, I think it's time to stop for today.